Hello, and welcome back to the web series Developing SPECTER using Innoslate's digital thread. My name is Mallory Jones, and I'm a systems engineer here at Spec Innovations. In the previous web series videos, I introduced the Break the Ice Challenge, previewed Innoslate's digital thread, and demonstrated the processes that initiated the Lunar Rover project. In this fourth video of the web series, I will demonstrate the research and work conducted during Task 1 of the Lunar Rover project. This task was crucial for determining the needs of the system in order to begin designing the Lunar Rover. To complete Task 1, research and design the Lunar Rover prototype, Innoslate's documents and diagrams views, modeling and simulation, and CAD viewer were utilized throughout the following processes in this web series video. In the Systems Engineering V model, this work took place during architecture development and system design phases. The Task 1 statement of work was broken down into 3 subtasks: research, design, and incorporate Innoslate's digital thread. From this task, a set of requirements, bill of materials, and final report were produced. For the purpose of this web series, Task 1 will be split into 2 short videos: research, then design, starting with research up first in this video. To kick off research for the Lunar Rover project, the NASA Break the Ice Challenge rules and documentation were investigated to extract crucial information, such as terms and definitions imperative to regolith excavation and Lunar Rover systems, technical constraints the system design must adhere to, environmental conditions that will impact the overall performance and success of the Lunar Rover mission, mission requirements as set by the challenge, technical and performance goals to aim for when developing the rover, and lastly, assets and equipment external to the rover system that will support its success. As stated in the NASA Break the Ice Challenge rules, there are 3 mission requirements to guide the design of the Lunar Rover system. They are excavate regolith at the excavation site, extract water from that regolith using the NASA water extraction plant or using functionality incorporated in the system, and deliver the extracted water to the delivery site. Performance goals and environmental conditions on the lunar surface were also provided by the Break the Ice Challenge rules to establish guidelines and constraints for the rover system. They will be defined and addressed throughout this web series. In Innoslate, these mission requirements and performance goals were recorded by going to Documents View, selecting the requirements document type, then choosing whether or not to use the provided template. For these mission requirements, I decided not to use a template and instead got straight to adding them to the document. A context analysis was conducted after important information and mission requirements were gathered from the challenge rules. An as-is system architecture was produced from an asset diagram by defining the existing equipment and systems that will be external to the Lunar Rover. These assets included ground communication on Earth that will collect data from the rover during its mission, a lunar lander that will transport the rover from Earth to the surface of the Moon. However, as noted before, only lunar lander dimensions and payload constraints will be incorporated. An excavation site and delivery site were also mapped out as provided by the challenge. This is where regolith is excavated and extracted water delivered. A water extraction plant and power plant have also been provided by NASA to convert the excavated regolith into water and provide power for the rover. In Innoslate, the external system architecture was produced by going to Diagrams View, selecting the asset diagram, then setting a background image of the Moon. Asset entities were dragged to their designated locations to represent each external system. Next, a Concept of Operations document, or CONOPS, was created to brainstorm and define the initial Lunar Rover system design. It outlines SPEC's proposed solution to develop a regolith excavation and water delivery system on the Moon. In Innoslate, the Concept of Operations was created by going to Documents View, selecting the Concept of Operations document, then choosing whether or not to use a provided template. For this CONOPS, I used the NASA Defense Acquisition template so I could quickly get started with the provided outline automatically generated for me. Once a rough concept of operations was designed and documented, a functional analysis was conducted to enable creation of requirements for the rover prototype to represent the Lunar Rover system. 2 diagrams were produced in Innoslate to assist the succeeding requirements analysis. These diagrams were the mission scenario action diagram and a hierarchy chart of the functional elements of the Lunar Rover system. This action diagram visualizes the lunar rover's mission on the surface of the moon. It steps through, in order of execution, all the actions the rover will perform during its mission. This diagram was produced using the mission requirements provided by the Break the Ice challenge. In Innoslate, the mission scenario was created by going to Diagrams View and selecting the action diagram type. Once a parent action was created for the diagram, a parallel entity was dragged to the blank user interface to create the various branches. Each action entity and its IO entities were also added in their respective order of occurrence to represent the actions to be performed by the lunar rover on the surface of the moon. The mission begins once the lunar rover payload is landed on the moon via the lunar lander. After landing, the rover navigates to its designated excavation site and begins excavating the regolith by swinging its excavator claw and digging at the lunar rock. The rover then deposits the collected regolith into its storage container until maximum capacity is reached. With the collected icy regolith protected in the storage container, the rover proceeds to navigate to the water extraction plant for the regolith to be mined for water. Once complete, the water is collected and protected from the environment in the storage container. The rover then navigates to the designated delivery site to store the collected water for the duration of the mission. This excavation, extraction, and delivery process occurs in parallel with the rover system monitoring its battery levels, collecting temperature and distance traveled data, and maintaining calibrated equipment. At the delivery site, if more power is needed, the rover will charge its battery before continuing on to the next exhibition. A maintenance check will also be performed to determine no equipment has been damaged by the abrasive lunar dust particles. Lastly, the updated water levels and collected distance data will be transmitted to Earth. Ground communication will receive the data and return a confirmation to proceed with the mission or command to end the mission. All these processes repeat until the goal of collecting 10,000 kilograms of water has been reached or 365 Earth days have passed. After mapping out the functions to be executed by the rover during its mission, a high-level functional hierarchy chart was then generated by categorizing each of the actions in the mission scenario. These functional categories were determined to be locate, excavate, transport, store, power, communicate, and retire. In Innoslate, the functional hierarchy was created by going to Diagrams View, selecting the hierarchy chart, then choosing action entities to be used for composing the breakdown structure. Each of the functions in the hierarchy were then decomposed using a top-down approach to discover all aspects of the rover's functionality. Once the mission scenario and functional hierarchy were developed, they were both used to derive a set of functional requirements from the mission requirements. Performance requirements were also defined using the specifications extracted from the Break the Ice Challenge rules during the initial research mentioned at the beginning of this task. In Innoslate, the requirements were created by going to the Documents view, selecting the requirements document, and choosing not to use a template. Each functional requirement has its own line in the document. Once they were all written, Innoslate's quality checker was run to evaluate each requirement against NLP heuristics. These attributes included clear, complete, consistent, correct, design, feasible, traceable, and verifiable. If any requirement had a quality score lower than 75%, then its attributes were investigated and the requirement modified to improve its quality. After the derived functional requirements were written and analyzed, they were traced back to their mission requirements using the derived by relationship. This was done by selecting the functional requirement, navigating to the side panel with the entity's relationships, and choosing to add an existing entity in the derives relationship definition. This detail and documentation enables traceability throughout the Lunar Rover project. Up next in the web series Developing SPECTER using Innoslate's digital thread is a video demonstrating Task 1 design. Thank you again for being here today, and I'll see you in the next video.